Okay, and here we are with present value. This is the other end of compound interest, and in this situation we're going to work backwards. And what we're going to do is we're going to try to find the original amount we need to get to some kind of future value later. So when you're asked to find the present value, you are being asked to find what you started with. So it's sort of like working backwards. But fortunately for us, finding that working backwards isn't too bad. If you take a look at the formula, account balance is equal to P times 1 plus I to the n. You can solve for P by dividing both sides by that whole set of parentheses raised to the nth power. And the other nice part about this is, since it's going to be in a denominator, you can give it a negative exponent, and that's the formula that we're going to use here. So it's going to work exactly like compound interest, except we're solving for the P, what we start with, the present value, if we have a goal in mind to get to later. So let's take a look and see how that works. If you want to save $1,000 over the next 2 years in an account that earns 4.5% interest compounded quarterly, how much should you initially invest? Okay, well, this right here, this is my future value. That's my A. But what I don't know is I don't know how much to invest at first. So what we're going to do is we're going to set up our formula for compound interest and see if we can figure out what that is. So our P is A times 1 plus I to the negative n. Okay, you have to pardon the cat. He wants some attention right now, don't you, kitty cat? Yeah, you do. Okay, I got to get back to work here. So now that I have this I and this n, that's what I really need to know. Because I know that my future value, my A, is $1,000. I know that that's what I need to have. And then my I is going to be 0.045, and if I divide that by 4, that's because I compounded quarterly. And now I need to work on that exponent, and that exponent comes from 4 times per year of compounding interest times 2 years. So we should expect that we're going to get paid interest 8 times. So my exponent for that is negative 8. So now let's punch that into the calculator here. And when we do that, we're going to wind up getting $914.39. So you see that we need almost all of this right away in order to get to $1,000 over 2 years. That doesn't seem like it's really all that helpful, that you're only going to get about 85 bucks of interest when this is all said and done. So pretty disappointing. But if you have more money to start with and maybe a higher rate, then you don't have to have as much. And also, if you do this over a better length of time. If you take a look at this example, you'll see why. Find the present value of $16,000. Okay, so again, this is our future value. This is our A. And I know this is over 9 years at 6% compounded semi-annually. Okay, so now that I know that information, I can go ahead and set up my formula to find the present value. A times 1 plus I to the negative n. Okay, so my A is $16,000, and then this is 6%, 0.06 compounded semi-annually, so twice per year, and then my negative exponent is going to be negative 18 because I have $16,000 that I want to get to after 18 interest compoundings. And I go ahead and I punch that into the calculator. And it's not as much of a percentage of the amount that I need, fortunately. It's $9,398.31. That's how much I need, so that way I can have this taken care of in 9 years' time. And that's how the present value formula works. Okay, now another interesting question would be, how much time do we need to get to that goal? If we know the rate but we don't know the time, that's an interesting problem in and of itself, pun intended. So how much time is it going to take for $2,450 to grow into 10 grand? at a rate of 5.25% compounded quarterly. All right, that's the initial setup that you see right there. And this X value is going to tell you the number of compounding periods. But there's a problem there. That number of compounding periods is in the power, and it's going to be really hard to figure out. So let's see if we can find out what that is. I'm going to jump in and use Desmos here because I think you're going to find out that's going to be a much better way of doing this, or your graphing calculator where you can find an intersection. I want to change my settings though, my window settings, so that way my axis is pretty easy to figure out. I want to go from -1 to about 150 on my x-axis, and then my y-axis I want to start at -1,000, and I want to go all the way up to well, my goal is 10,000, so I probably should make that 12,000 as I go along. Okay, so that's a good view of my window here, and you'll see why I chose 150 in just a moment. So what I'm going to do in my first one is I'm going to type in y is equal to, and then I'm going to type in that function that has the compound interest. Now, lucky for us, Desmos is pretty easy to type things in, and if you want a power, you hit Shift and 6 to get that upward pointing arrow, that caret character. And there you see, that's my exponential function that shows how quickly that money is going to grow over time. And then eventually I want it to get to $10,000. Okay, now, if you remember from systems of equations, you will know that the point where they meet, that is the point where it solves the system. And the x value tells me the time. The y value tells me the money. The x value tells me the time. So after almost 108 compounding periods, I'm going to end up with $10,000 in my account. 108 compounding periods, that's a lot. I mean, you probably stop and think and you say to yourself, oh my gosh, that's like 108 years? Well, no, not really, because remember we compounded quarterly. So 108 compounding periods divided by 4 is going to give me, well, 27 years. Trust me, I don't know if it's going to be worth the wait. I might be able to find an investment that gets me up to 10 grand a little bit faster. I just hope it wasn't a Ponzi scheme or something like that. Okay, let's take a look at another example where we could look at this as doubling of the price, and that's happened a lot. You know, this may not. It seems like, you know, you think about like the rate of postage stamps or something like that. The joke used to be that they would double the price every other weekend. Well, they haven't done a lot of price raising, fortunately, in recent years. It's been pretty incremental, but I remember when postage stamps were 10 cents a piece, and now they're 50 cents each, and holy moly. So if the price of a gallon of milk is $3.75 today, and the inflation rate is 6% per year, how long is it going to take for that price to double? We can do this one of two ways. The first way is the way that we just talked about, and that's to find the time. So this is my P, the original amount, and the double price is going to be my A, and I know my rate, and fortunately it's per year, so we don't have to worry too much about division in this problem, which is good. So double the price gets me $7.50. And if I want to find out how long it's going to take for that price to get to $7.50 from $3.75, I can do exactly something very close. So I want to change my settings again, because now I don't need something as large. I might need, you know, like maybe 15 or something like that on the X. And I probably want to go to maybe $10 on the Y. And I know that that's $7.50. And I also know that my original amount was $3.75. And then I can just change all of this because it's a 6% rate. Okay, and now that I've got everything set up here, I can click on that point once again, and I notice that it's almost 12 years. for the price to double when we're raising things at a rate of 6% per year. Now, something interesting springs out of this, and that is what is called the Rule of 72. And financial analysts use this all the time to try to determine how long it takes for you to double your money. And the Rule of 72 works like this. If you know what the interest rate is, and you know you're going to get that consistent interest rate over time, you take 72 and divide it by that interest rate without converting it into a decimal. And you get about 12 years for the price of something to double. That's pretty interesting how that it works out in that regard. It's kind of a strange rule, one of those interesting mathematical coincidences. Some people go by the rule of 70, which works in the same way, but 72 is something that I remember quite a bit. Okay, so for our last example here, how long in years will it take a car to double in price if the automakers raise prices 3% each year? Well, if they raise the prices 3%, I just take 72 and divide it by 3, and I'm going to get 24 years for prices to double. Now, just between you, me, and the fence post, cars have more than doubled in price in the last 24 years, or so it seems. That's just me talking now. Okay, so there is your information about some more things with compound interest.